I'm done with all the administrative stuff. We can discuss what you want to discuss now. Oh, there's a question. Simulators that we should use for our projects. Okay. At some point, could you say a few words? Alexei says, could you say a few words on simulators that we should use for our projects? Also, would you encourage or discourage using real hardware, particularly dev boards privately available? Thank you. I'll respond to that right now, I think. So this really depends on your project. What kind of simulator you will use, what kind of emulator you will use depends on what kind of project you will do. We will provide a list of some simulators. I don't know if that list is ready yet. Probably not, right, Tyler? Oh, okay. Okay, Hongi is making it. So we'll provide a list of simulators that you can potentially use in computer architecture. And I'll tell some of them right now, I guess. Okay. So basically, what I wrote is PIN and Multi2Sim. These are two simulators that are relatively easy to use. So a lot of simulators have this functional simulation and timing simulation that are decoupled. What functional simulation means is you take an executable, you take a binary, and it basically models the execution of that binary. You can actually get a trace out of this functional simulator, or you can get an instruction out of the functional simulator. You do an add, let's say R2. Basically, it models the execution of this add. You can execute the add, and it tells you that R2 will have this value, right? You can do a branch based on, I don't know, maybe R2 equal to 0, let's say, and a target. Well, R2 doesn't go anywhere, of course. Basically, you test whether R2 is equal to 0, and if that's true, you jump to a target. This executes the branch, right? It tells you the correct result, as if the program will execute. So this is really architectural modeling, as I showed you earlier, that you didn't see on that little sheet of paper. Now, once you have this, you know everything about a program, right? About the dynamic execution of a program, because there's an input set into the executable also. Now what you can do with it is you can certainly analyze the program, right? You don't need to do timing here. You can, for example, count the number of branches that are taken. And PIN is great at that. So PIN is one example of a functional simulator. You can instrument every branch in the code and figure out what fraction of the branches are taken, actually. Right? You can do that. I'd encourage you to do that. And actually, PIN itself provides some routines that already do that. That's one thing you could do. You can discover different things about a program. But another thing you can do is actually you can use this information to drive a timing simulator, which models a pipeline, let's say. And here, basically, you can simulate anything you want, right? Simulation is like a field of dreams, in my view. You can dream and you can simulate. And of course, you can cheat also while dreaming, unfortunately. So you got to be careful. This enables you to explore many different potential architectures over here. Like you can actually model a 1 terabyte cache, right? And see what's the hit rate in that cache. Basically, when you get a load instruction over here, you have an address, because the functional simulator already generated that address. And in the timing simulator, you don't necessarily use that address. Let's say you have fetch, decode, you wait for the rename, and you wait in the reservation stations, and then you have a schedule stage, which picks the instructions that are ready. This is an out-of-order engine, right? Here, you know the load address. How can you cheat? Basically, by knowing the load address, you can, at the fetch stage, you can actually use that address for something, right? But you don't want to do that if you're modeling things accurately. So basically, you model the execution of the load. When the load executes, you use that address to model the cache, right? Maybe I'll pull this up for a while. I don't think we'll need that. How do we do that? Power off? No. I just want to have the screen up. Oh, you have? You know how to do it? OK, I'll let you do it while I explain. So you can model the cache over here. And basically, the cache takes the address, and you model the contents of the cache, the tag store, and maybe the data store. If you just want the timing, you may not need the data store modeling, right? But if you're doing something else, like trying to model how cache compression affects performance, you need the data values because you're compressing the data values, right? So there are subtle things like this. Modeling, what you model depends on what you want to accomplish also, right? You may want to model the data store, you may not want to model the data store. There are disadvantages of modeling the data store, right? Now it's more expensive. Now your trace needs to contain the data also. And not only this data, but also all the data in the memory image, right? So basically, you can do anything you want in the timing simulator. So you got to be careful as to how accurate you want to be. I'll get back to that actually. Maybe I'll write it over here. There's this fundamental trade-off between three things in simulation. Well, I'll get back to that. That's to remind me. So at the end of the timing simulation, basically timing simulation, what you can do is you can take one instruction and model it. And now, because of this decoupling, you can do things like branch prediction. Nice. You can actually model the wrong path execution. For example, the functional simulator, but they need to now interact. So functional simulator executes a branch. And the branch, let's say, you need to model the timing as to what happens, as to the processor you're building. It inputs that branch into the timing simulator. Now in the fetch stage, you model a branch predictor, right? The branch predictor says taken or not taken for this branch. Now the next instruction you fetch is really dependent on this prediction, right? So your functional simulator, if you want to model a processor as it really operates, needs to interact with the timing simulator. So the timing simulator needs to tell the functional simulator, this is the next instruction I want to fetch. Because your branch predictor may be different, right? So that's when the interaction happens between the functional and the timing simulator. Timing simulator says, next instruction you should give me should be the fall-through path of the branch, right? And that could be incorrect. So at this point in time, you actually know what's the real branch direction. This branch is, let's say, taken based on the functional simulator, based on every other instruction that is executed. But the timing simulator, the branch predictor that you're modeling in this engine says it is actually predicted, not taken. Which means that the timing simulator should redirect, should say to the functional simulator, the next instruction is the not taken path. Now, you model all of those instructions that are on the wrong path. Basically, functional simulator provides those, right? You model them, and at some point, this branch is modeled. And that branch, you're modeling just the timing, right? Basically, that branch is executed depending on the data flow order. And when it's executed, now you can say, oh, the prediction was taken. Oh, the prediction was not taken, because you record that at the fetch stage. But really, this should be actual direction is taken, which means that I've actually mispredicted this branch, right? Actually, you knew that all the way along, but you didn't act upon it, right? You actually mispredicted this branch. Now you act upon it, and you basically model the flush of the pipeline, right? So you wasted a bunch of cycles, and you modeled how many cycles it took to flush the pipeline, right? Now time is, of course, you have a cycle count somewhere over here, and that time is incrementing. Basically, you're really modeling the execution time of the program. Now, of course, at this point, there needs to be another interaction, right? From this point in the timing simulator, you need to redirect the functional simulator, because the branch has resolved now, and the timing simulator tells the functional simulator, now you got to give me the instruction at this target address, right? At the branch target. Okay? So how do you actually do that? Well, you need to get the correct state also, right? So you need to actually go back to a point, because you've executed a lot of instructions in the functional simulator. Your branch was here, and you executed on the wrong path I don't know how many, 100 instructions maybe, right? So you really need to go back to this point and start re-execution from the target program counter of the branch in the functional simulator. Does that make sense? So that's how you model wrong path with this decoupling. So this is the most accurate, this is a more accurate model, right? Alternatively, you can actually generate a trace. You can really decouple this. Here, functional and timing simulator are running together at the same time. And Multicore does this, I believe. You could design a simulator with pin that does this. But you could also alternatively decouple these and run them at different times. So you can have functional simulator, you run the program and generate a trace with all the information that you need about every instruction. And then later on in time, you take that trace and feed it to your timing simulator. Right? Now the trace is stored on your disk. It could be waiting for years. And years later, you decide to simulate the timing on some machine. Right? This is also a powerful way of doing simulation. Well, this is more called trace-driven simulation, actually. In this case, instruction trace-driven, because you can actually generate a lot of information about instruction traces. Now, what you cannot do with this is, well, what is harder to do with this is what I described over here, wrong path modeling, for example. Right? Here, you have a trace, and this is all the dynamic instruction that should be executed. Right? For example, when you go to a branch, the next instruction is always the correct target of the branch. So you don't have the wrong path information, right? So you cannot, the timing simulator can figure out that, oh, this branch is mispredicted, but it doesn't have the information about what to execute after that. So usually one thing that people do is to insert no-ops. Now that's not an accurate model of wrong path, but still, it's better than always predicting correctly, right? So there are multiple options you can imagine. So that brings us to this over here, accuracy, flexibility, and performance. So no simulator is really perfect. And it's really an art to design simulators, in my opinion. And you always make this trade-off, accuracy, flexibility, performance. And sometimes you intentionally model some things inaccurately because it takes performance means basically simulation time, right? So you're a designer trying to make decisions about what to put into your next processor. Do you model everything in that processor very accurately? Right? Do you model every single cycle of execution? Well, if you do that, the simulation time increases significantly, right? And your flexibility reduces. So if you increase your accuracy a lot, your flexibility reduces, and your performance, simulation time, well, I guess I don't like this one, because one is the opposite of other. I guess performance is 1 over simulation time then? Your performance reduces also. And this affects a lot of things, right? This affects time to market of your processor, for example, or whatever you're designing in your system. Maybe I'll just do simulation time over here because I'm getting confused myself. Sometimes it's best to pick the thing that goes the way you want to go. And I want simulation time to increase when accuracy increases. OK. Right? Now, so there are cases in the simulator you may not want to model. Basically, you really want to, if your flexibility reduces, so if you model everything in a cycle accurate way, for example, if you model the access, pipeline access to your cache, your flexibility also reduces, right? So there are levels of abstraction. You can actually model every pipeline register that you're going to build. Or you can say, I don't care about the pipeline registers. I just say, when I get this load, it just takes 3 cycles to actually access the cache, right? That's a higher level, more abstract model. Now that 3-cycle model is much more, so I guess more abstract model versus much more accurate, I guess cycle accurate, I'll say. This more abstract model is more flexible. You can always say, oh, I'm going to change the cache access latency 2 cycles, right? You just change a variable that says cache access latency. Whereas here, with the cycle accurate model, it's not that easy, right? You've written the RTL, let's say, register transfer level hardware design. Now you need to really add that pipeline register. You need to add the stall signals. You need to make it work, right? Now if you try to do that, you're losing flexibility. And you're increasing your simulation time. But you're being more accurate. So you always have this trade-off in simulation. And if you want to actually test the ideas quickly, you would like to be less accurate. That enables you to be flexible. That increases your simulation time. But you've got to be careful as to what you don't model, right? You don't want to reach the wrong conclusions. That's why this is an art. Does that make sense? Yes?
So the accuracy difference mainly comes from the branch prediction.
So that was one example. That can come from branch misprediction. But it really can come from, for example, you may not want to model some instructions. Because those instructions require a lot of modeling, right? So, for example, in x86, there are a lot of weird instructions, if you will, where you load the task tables, for example, task table management instructions. You may not want to model that accurately, right? But when it comes, you need to execute it, right? You can say this takes 50 cycles, right? That's inaccurate modeling. But if it doesn't happen frequently, that doesn't affect the entire execution time. And you haven't devoted all that time to actually accurately model an instruction that doesn't happen often. So that's another example. Another example, you may not want to model your memory controller very accurately, right? Because memory controllers are very, very complex to design, actually. For example, you can say, I'm not going to model refresh, right? There will be some systematic error in your modeling. But hopefully your results will be correct. But this depends on what you're doing, actually. If you're proposing an optimization that changes refresh, you probably want to model refresh. But if you're evaluating an optimization that really doesn't matter, where refresh really doesn't matter, it looks like noise, then you might want to not model it, right? So it's important to be careful about what to model and what not to model, depending on what you're changing in the system. Say it again.
So, for example, if there are some weird instruction and we do not want to accurately model them, so we just give them a very brief modeling in the timing simulator.
That's right. That's right. Exactly. Because functional simulators should execute it, hopefully. But even functional simulators sometimes have that. Actually, sometimes, even with functional simulators, there are inaccuracies. Now that's harder to fix, right? So you really want to get a good functional simulator.
So how about a PIN? Is a pure timing simulator?
So PIN itself is a functional simulator. PIN itself is really a virtual machine. You can actually take your program and attach it to PIN. It'll run slower because it's really attaching to your program and attaching to your executable and running. So you may not. Even if you don't do anything, even if you don't instrument your program with PIN, it'll run slower because it's attaching to your program. So it's a functional simulator. If you can instrument every instruction and get a trace. But PIN, I think they call it PIN tools, right? You can write a PIN tool that can actually gather information and model some kind of timing. Okay. Okay. I think I've gone down longer than I thought I would, but hopefully this is interesting, right? Because this is actually how you model a lot of things in architecture. If you come up with a new way of doing, let's say, eliminating refreshes, you'll need to model it somehow, right? Because existing hardware cannot do that. Or another way of designing the out-of-order execution engine, right? You will need to model it this way. And you will face these. So the question though is, what other simulators exist? What other simulators exist? I guess there are some other simulators. One is Gem 5. Is it called this way? Yeah. That's another simulator that's public. That's a little bit hard to use, in my opinion. I don't know. They made it easier to use, but the last time I looked at it, it's hard to use. So you can take a look at it. I think we'll come up with a list, a longer list, and we'll try to recommend you some simulators. But talk with us. It'll really depend on what you want to do. So the second part of the question, I think, was, let's see. I'll have to find the question, but
would you encourage or discourage using real hardware?
Yes, that's right. So OK, that also depends on, thanks, Brian. That also depends on what you want to do using real hardware. So using real hardware could be FPGAs, for example. There you can model a lot of architectural changes potentially, because you're actually reconfiguring the hardware. If it's a development board, you're much less limited. You're much more limited as to what you can do architecturally, right? Because let's say you have an ARM development board. Can you actually modify things in the architecture and test in the software? Potentially, it could be powerful, but now you cannot modify the processor in there, for example, right? It's not clear if you can modify the memory controller. It depends on the development board. If it's an FPGA-based memory controller, you can potentially do it, right? So development boards are usually more limited in what you can modify. Okay? But this really depends on the project you would like to do. And I'm open to different types of projects as long as there's a strong architectural component to it. And it's a substantial project. Okay. Okay. What else? I guess let's see. Does anybody want to talk on the other side? We could test that too. OK, I guess thank you. Any other question? Yes?
I have a question about the Sun Rock system. So it didn't make it to the market because they're trying to implement transactional memory, and that just took them much longer than what they expected. But it's really interesting the Scout model they're using. Do they have any like real workload that's just not like some test or some 1 or 2 graphs, but like real model of how well it works?
OK, the Scout threading, as they called it, which is run ahead.
Yes.
And they added other things on top of that, actually. They called it simultaneous, not redundant. What do they call it? Simultaneous speculative threading, SST. That's right. So this was part of lecture. Which lecture? We talked about it, actually, in the Multicore lecture, if you remember, when we talked about the Sun Rock processor. So I think, first of all, it's not clear why they didn't make it to market. Some wasn't doing well. Maybe it wasn't due to technical reasons. Transactional memory took them a while. That's right. So they have some analysis of the Scout threading. Let's see. Oh, I guess I'll have to pull it. Scout threading, simultaneous speculative threading. So Scout threading is run-ahead execution, basically. Sun's version of run-ahead execution. When you get to long latency cache miss, in their case, it was an in-order processor, so long latency cache miss is any cache miss in the L1. Checkpoint the architectural state, go into a speculative processing mode where you can now execute independent instructions of the cache miss, but dependent instructions, you mark them somehow and defer them for later execution. And you execute the independent instructions, and the independent instructions can now generate other cache misses that you can serve in parallel with the original cache miss. That's the idea of run-ahead execution, right? And Scout execution is essentially that, basically. But Sun did more than that, which they called simultaneous speculative threading. And in run-ahead execution, when we proposed it, for example, this was my PhD thesis. So I like this idea a lot for some reason. You should do your thesis on an idea that you like a lot. Like, you should be excited about doing a thesis, first of all. And I still like it for some reason. But basically, when we propose it, you get to we basically drop the instructions that are dependent on the cache misses. That's regular run-ahead execution. Now, what you need to, the implication of this is when you actually are done with run-ahead mode, when the original miss is done, you need to re-execute everything, right? Because you've dropped some instructions in the middle. So you go back to the beginning. So what Sun did with this one, simultaneous speculative threading, is instead of dropping those instructions that are dependent on the cache miss, they deferred them. They put it into a queue. Let's see if it exists here. Yeah, there you go. I cannot see it, but maybe you guys can see it. Oh, now I can see it. It's bigger. Yeah, it's here. Yeah, basically, this execution pipe figures out whether an instruction is dependent on a cache miss that you didn't service yet. If it's dependent, that instruction goes into this deferred queue. And once the cache miss completes, that instruction can now execute again. So you can think of this as you have two threads. You have a single thread program, and you've divided the program into two threads, right? One is executing instructions that are not dependent on the cache miss, and the second is executing instructions that are dependent on the cache misses. And that's happening in parallel, right? It's a speculative parallelization method. I think I actually talk about this in the speculation lecture too, a little bit. So it's nice because now you don't need to flush the pipeline. It's a little bit different from run-ahead mode. So I think it's an improvement over run-ahead. And your question was, like, is there more analysis of this, right?
I found it in the paper.
Oh, you found it in the paper? OK, excellent. So this paper is all about that, basically. It analyzed it. It may be a little bit difficult to read. It's not that easy, I think. If you read the run-ahead papers, it makes it easier. But it does have that analysis. I know there is one figure. This actually I showed. Yeah, this shows basically how it is executed, how this code fragment is executed in this engine. And this, for example, shows you when you take a checkpoint and what is deferred and what is not deferred. I'm not going to go into this in detail, but if you're interested, this is a good paper that details that. And the analysis you wanted is somewhere in the results.
Yes, it's page 10.
Page 10, OK. Let's take a look at that too. So they basically model all of this in a simulation. If you look at this, there you go. Results were produced by an in-house cycle-accurate simulator capable of simulating SST and the other architecture studied in this paper. You'll find that a lot in computer architecture, because how else are you going to build this, right? You could, another way of doing this is actually taking an FPGA and implementing all of this in RTL. Now that's good when you actually want to get accurate results. But if you're doing design trade-offs, for example, should I do run-ahead? Should I do this? Should I do that? Should I have a bigger cache? Now that's tough, right? You cannot build hardware for every single configuration, right? So they use this simulator. And of course, when you use simulators, how do you actually test your workload is an issue also, right? How many instructions do you simulate? Because this is still slow. Actually, software simulation is slow. You'll see many papers simulating hundreds of millions of instructions. Right? Then, how are those hundreds of millions of instructions representative, right? Like, what are you testing? That's important also. So there's sampling-based simulation. What it does is it basically it basically runs through the program. It does some functional simulation, and then it does some detailed microarchitectural simulation for maybe 10,000 instructions. And then it runs a little bit more, and then it does microarchitectural simulation for 10,000 instructions. So this way you can sample the execution of a large workload. That's what this paper is about. This was actually Tom Minish's thesis here at Carnegie Mellon. He proposed some sampling methods to do simulation. Actually, his thesis was not on that, I think. But that was one of the papers he wrote while he was here. His thesis was on memory streaming. So you can do different kinds of simulation. One method is doing the sampling. You have the entire workload, and you sample points in it and simulate those points, those short points. The other method is basically figuring out what's the most representative portion. So how do you do that? You can run the program using functional simulation, and you can figure out what are the representative points in the program. What is the most frequently executed basic blocks, for example? And you model you fast forward to that part of the program in dynamic execution, and you model, let's say, 100 million instructions at that point. That's another way of doing it. It's not sampling anymore, right? You kind of pre-filter what you model. So you try to focus on the most commonly executed code in your program. So in this case, they use the sampling approach. Is this the one you were looking for?
That's one.
OK. Speculation failures. Yeah, so if you're interested, I'd encourage you to look at this way. This is the result I had shown in the lecture, actually. So here, for commercial workloads, they show the performance improvement over stalling. This is basically when you stall over when you get a cache miss. Right? And Hardware Scout, this is actually run-ahead execution, basically, in their model. So you gain some performance. SST is simultaneous speculative threading, which is what I just described. And OOO is out-of-order execution. And I'm sure there's a window size they model over here. So what they're showing is run-ahead buys you similar performance as out-of-order execution, at least in this kind of workloads. But it's much simpler, hopefully. And simultaneous speculative threading buys you some more performance. What I would have liked to see in this graph is actually out-of-order execution plus run-ahead also. Right? That would have been nice as a comparison point, right? Because run-ahead is an idea that's independent of the model. SST is actually dependent on the in-order execution. OK? Does that answer your question? You may want more detailed analysis that's not necessarily in the paper.
Actually, could you go down a little bit?
Sure.
This graph is more interesting.
OK, there's another interesting graph. Let's see. This one?
Yep.
OK.
The scout in this graph suffers a lot.
That's possible, yes. Suffers on some benchmarks, right? Like this one. Hammer. Yeah. Yeah, this could actually be an interesting project idea also. Why do you think that's the case?
Maybe it's the type of stalling that doesn't lend itself very well to running ahead.
Mm-hmm. That's right. Maybe run-ahead is useless, right? Basically, you're executing a lot of these instructions. And then you're flushing the pipeline, so you're losing performance, right?
Which I'm assuming is why you have lower than 0%.
Exactly. Yeah. So that could be one reason, because you're flushing the pipeline. Otherwise, you would have kept those instructions in the pipeline, and you would have had better performance.
Also, you might be polluting higher level caches.
Mm-hmm. That's right. So that could be another reason, right? Because when you run ahead, when you do this hardware scout, you may not be you may be executing instructions that you don't want to execute, right? Why? Because what might happen is you can get to a branch misprediction, and you may not be able to resolve it because it's dependent on a cache miss. Now you're on the wrong path. And that wrong path may access both instructions and data that you're not going to use later. And you bring them into the caches. Now you're polluting your cache, potentially evicting things that you're going to use later. Right? So that could be another reason. Another reason is this is a multiprocessor system, 8P, right? 32P. These speculative requests, even though they may be accurate, they may be causing contention with non-speculative requests. Right? Because some threads are in run-ahead mode, some threads are not in run-ahead mode in this case. And because of that contention, the threads that are more critical can get delayed. Right? This is similar to what we've seen resource contention problem. So that could be an effect over here. So that's why you may be seeing performance loss. This actually, if you're interested in doing a project, I'd be happy to recommend projects related to this, given that this is so close to my heart. I can give you very concrete projects here. But one thing that has not been examined as much is how does run-ahead-like mechanisms or SST-like mechanisms, how do they behave with under contention when you have multiprocessors and different applications? How do these affect contention? How do these affect system performance? And how can you design better mechanisms to take advantage of that in a multi-core system? Run-ahead in a single-core system has been examined a lot, but in a multi-core system, it hasn't been examined as much. And how can you do it more efficient also? So we've looked at mechanisms to make it more efficient. For example, cut out those periods that are not useless. This efficient run rate execution that I mentioned in the lecture. If you're interested in that, I would recommend taking a look at that as well as this paper. Yeah. So floating point performance is actually better over here, right? Yes?
I have a question in the context of asymmetric systems. So it's like more, what is your opinion? We have like actually one large core that executes like, one large core and small cores inside. What do you think of replacing the small cores with FPGAs? So what is your idea about it, and what do you think? Is it like brand new or infeasible, realistic?
Sure. So that's a good question. The question is, you have an asymmetric system, and we've talked about large core and small cores in the lecture. One large core or multiple large cores and many, many small cores in the lecture. And the question is, what do you think of replacing those small cores with FPGAs? Actually, I think replacing may not be the right word, but adding an FPGA core, if you will, in addition to what you have, could be interesting. So I think going forward, like I motivated in the heterogeneity lecture, it's difficult to scale the performance and efficiency because applications have different requirements. And even within an application, you have different requirements in terms of performance and energy efficiency. So it's good to look at all of these different acceleration mechanisms. And I see large core as an acceleration mechanism. If you can parallelize your code with small cores and it executes greatly, that's great. But not everything fits there, right? You sometimes need higher performance. That's why you have this large core. Now, can you have other accelerators? So we already have such accelerators today, right? A GPU, for example. Some codes are better fit for GPUs. Some codes are better fit for a video decoder, specialized video encoder, video decoder, right? That's very specialized now. Now, FPGA and FPGA reconfigurable logic as a core itself provides another thing that enables you trade-offs, right? So I think it's definitely good to examine that going forward. What can you do with that? For example, maybe there are some portions of code that are very repetitive in your program. If you find that, but dynamically or statically, somehow through the compiler or while you execute your program, you can say, oh, this portion of my data flow graph and control flow graph, I'm going to map it to the FPGA. And when I get to it, I'll have a hook. When I get to it, I'll basically transfer control to the FPGA, which hopefully is tightly coupled. And then that portion will be executed very efficiently in the FPGA. Right? So I think going forward, those mechanisms will be more and more interesting and practical too. Why practical? I guess one of your questions was, would it be practical, right? I think it would be practical because it really depends on the benefit you would get out of this, right? If you get a lot of benefit, initially in the specialized systems, this could be a good way of getting performance and energy efficiency. And actually, like SoCs today have video accelerators, right? You have different kind of accelerators, and they're fixed accelerators today. But you could imagine implementing different kinds of accelerators with FPGAs as well. So going forward, I believe that will be practical. But I don't think they will replace the simple cores, because simple cores have their points in the design where they're very useful, right? Because if you can parallelize your program with simple cores, that could be more efficient than an FPGA because you're not reconfiguring anything. And you can actually parallelize even more. And also, you have better memory access in the single cores, which is a problem with the FPGAs, today at least.
Yeah, but there's some implementation like core run, for example, for memory controllers. You can do like many things with FPGAs. So now there's a bottleneck with small cores and even large cores. We're like stuck with really innovative solutions, but it's there's a bottleneck somewhere. And maybe with FPGAs, with new solutions, then you will overcome the bottlenecks we face at the moment with small cores and large cores. So
Yeah, potentially, that's right. It's good to definitely examine innovative solutions. I agree. And I'd encourage you, if you want to do a project related to that, that could be good. Yes?
And so Akash asks, what about using more than one core to distribute critical sections in ACMP?
Okay.
What's the trade-off in that case?
Yeah, let me try to get to that question over here also. I'd like to be able to see. I'm seeing better now. Yeah, more than one core to distribute critical sections in ACMP. What are the trade-off in this case? Yeah, I think that's good to examine also. I think I briefly mentioned that maybe in one of the lectures. But what accelerated critical sections does is it basically ships all of the critical sections to one single core, right? I think Akash's suggestion is you don't nearly have to have that large core, right? One of the benefits of the large core is there are multiple benefits. You can accelerate the critical section execution, but you also keep the shared data in one place, right? You could potentially imagine a design. I think what he's proposing is you say these critical sections go to this core, these other critical sections go to this core, these other critical sections go to this core, right? So you basically distribute the processing of critical sections to different cores. And if you do that distribution nicely, now you can keep the shared data locality. And now you can utilize those caches much better, right? With a single core, shipping critical sections to a single core forms a bottleneck because every critical section goes there, right? If you do that distributed processing, you eliminate that bottleneck. But you may lose locality a little bit, right? You got to be careful as to how you distribute. Now, presumably, a critical section is associated with a data structure, which means that the shared data that you're touching with the same critical section is the same or similar, at least, a superset of a superset. But critical sections that are different are hopefully not touching the same data structure, right? Now that's not always true if with nested locks, right? So this idea could work, I think. And I think it could be good to examine. It could reduce a bottleneck that exists in accelerated critical sections. OK, no more questions from Akash. Did that answer your question? Let's see if he hears me. OK, he's typing.
We can
Still
enable his microphone if you
Oh, OK. How do you do that? We can. OK.
enabled it.
Let's see if he wants to speak. We'll test this also. Do you want to speak, Akash? OK, when he speaks. Oh, OK.
I'll turn that down.
Hello? OK, now you don't want to speak. That's fine, thanks. We can try it some other time. If you want to speak, you feel free. Yes?
I want to show something interesting regarding FPGAs posted here. I couldn't find the paper he was referencing to. If you go to the website, it shows some data regarding using FPGAs and then comparing their performance versus other implementations.
OK.
I think according to this graph, it's sort of hard to justify right now using FPGAs because the gain between using FPGA and using other hardware is within 10x of each other.
OK.
Even compared to like the slowest x86 core. So it might be hard to justify going through a lot of extra trouble and forcing users to, or at least some type of users to compile in FPGA or ASIC in order to achieve a 10x performance on some parts of your program.
Potentially, it really depends on the application, though, right? Yeah. I don't know what application this is, and I can barely see this, but I assume this is for some kind of graphics
It's
workload.
comparing, performance per area per energy
Uh-huh.
of FPGAs to GPUs
And ASICs.
and ASICs. Yes.
So which?
Offline is ASIC.
Oh, top line's ASIC. So this is kind of expected, right?
Right.
As you specialize your hardware, you get much better pseudo gigaflops per millimeter square, whatever this means. But it's probably some
Better area, like perf per area.
yeah, performance per area. So that's the specialized hardware. So you get 100x or more than 100x.
Almost 1,000x
Okay, 1000x, where one is,
is baseline, pretty much.
what is the baseline? Do you remember?
No, because I can't find the paper.
Okay, where one is some baseline,
Some baseline,
basically.
yes.
And this, I mean, fundamentally, this sounds reasonable, right? This bottom curve is Core i7, huh?
Yes.
Okay, this is Intel's Core i7 for some workload that I don't know, for some graphics workload. So that's also reasonable, right? This is a very general purpose machine.
Right.
So your performance per area for this workload is very low. And in the middle, you have some things that
GPUs and FPGAs.
GPUs and FPGAs that are really close by, according to this, yeah, for this workload. This is actually interesting, you think. And here, there's the energy efficiency graph. So if you look at this, again, specialized hardware is much better than general purpose hardware. This is a good reason for specialization, actually. And that's an ASIC. And this is an FPGA, and these are GPUs. So FPGA is much more energy efficient in this case. So it doesn't sound too bad to me.
It's not too bad, but I think the game is not enough to push the
I see.
industry to say, let's use FPGAs now instead of maybe adding extra ASIC chips.
Yeah, maybe. But then the downside of ASIC is it's really costly, right?
Right.
There's cost is not shown here.
Exactly.
Yeah. I think it's going to become increasingly more costly to do ASIC chips. But you could have specialized accelerators, of course. That's kind of an ASIC chip on a chip, right?
Put something like an SoC or like a image processor
Yeah.
or something like that.
That's right. But FPGAs still get you, at least here, in terms of pseudo gigaflops per joule energy efficiency, still get you quite a bit, right? Yeah.
I think the problem is that FPGA is the area cost is a little large. So
Uh-huh.
that's why
That's why.
the number seems similar between
Yeah.
you.
Because your area is really general purpose in an FPGA, right? Because it can, you can program it to do anything. Whereas area in an ASIC is you're really optimizing the area for your problem. That's expected also. But this still shows some good promise, I think. But there's always a trade-off, right? This is for this workload. Maybe some other workload will show different results. The upside of FPGAs is you don't need to design an ASIC for every single workload you see, right? So there's that trade-off. This is a very similar trade-off that I talked about. Flexibility, performance. I guess accuracy doesn't count over there, but your flexibility, as your flexibility increases, in this case it's different. Okay, as your flexibility increases, your performance reduces, right? In this case.
Yeah.
But I think this is doing these studies is interesting, and maybe these will be recorded, right? So people can look at this offline, and if they're actually watching this later on. Okay. Yeah. So I think one of the issues with FPGAs is programming model, right? Programming is not easy for everyone. So solving that will enable FPGAs to become much more powerful in the future. That's a tough research project, though. Don't propose that as a research project. Propose a more concrete one.
Actually, there's OpenCL for FPGAs,
Uh-huh.
even MATLAB now converts like the HDL code to, MATLAB to HDL.
Yeah. So that's right. And people have tried to do that a lot, right? That C2 gates also, right? The conversion is usually not very efficient. I don't know about the OpenCL implementation.
Try it.
Yeah. Oh, you need to try it?
Yeah.
Okay, yeah. Try it and let me know. But usually, that's been the dream of many researchers in reconfigurable computing for a long time. Basically, can we write a very high-level program, C, Java, and compile it down to the gates, right? Reconfigure the FPGA. There's been a lot of progress in it, but still the efficiency that you get in terms of area and performance is not as good as what an RTL designer would do.
Yes.
So I have a question on the data flow system. So from the microarchitecture view, so it contains, I remember it contains two major components. One is the code block, which is executed in the auto execution manner, and the other one is a window. So
is what? Sorry.
So it's a window. So auto execution. Okay, yeah, it's a time cache. It's a block. So you can issue the instructions in a time cache in a time matching manner.
In what manner? I couldn't hear that.
Tag matching.
Tag matching. Okay,
yeah,
tag matching.
Yeah. So my question is about that. So what's the difference between this microarchitecture and the one we mentioned in the lecture? So non-data flow execution system.
I see.
Yeah.
So
yeah. For example, so is it possible for us to just compile an application in the data flow compilers and just run it on traditional microarchitectures?
I see. So I think, let me try to clarify a little bit. So your question is about data flow in general. Today's architectures, like out-of-order execution, is really a restricted data flow architecture. It's really sequential execution, one Neumann model at the programmer level, at the architecture level. But underneath, it's microarchitecturally, it's restricted data flow. Because what you do is very similar to data flow, right? You put the instruction into the reservation stations, and when an instruction produces its result, it broadcasts the result, and all of the instructions that are dependent on it capture the result, and now they can execute. Yeah. So in a sense, those nodes are instructions, and they fire when their values are available, which is the principle of data flow, right? I think what you're asking is, data flow could be architectural also. Is that correct? Basically, your programs could be data flow. Your program itself can say, this instruction should enable this other instruction. Right.
Or just put some application, put some source code and compile it with the data flow compiler and just run it on the traditional microarchitecture. So why do we need data flow specific microarchitectures? Is there any difference between data flow
at the programming level versus data flow at the architecture level?
Microarchitecture
Microarchitecture
level.
level. So let's ignore the case where data flow is architectural, because that doesn't exist today in existing systems. But people have tried to propose that. Okay. But I think what you're saying is data flow at the programming level and data flow at the microarchitecture level. So it really depends on what kind of programming model you have at the high level, right? So you can certainly do that, but the microarchitectural level data flow, the benefit that it would provide is really the irregular parallelism that you would extract. That's always the benefit of data flow at the microarchitecture, at the low level. So for example, at the programming model level, you may really not know the cache misses, right? Yeah. But at the architectural level, when you get a cache miss, the dependent instructions wait, right? And you can execute the independent instructions, right? Whereas you cannot do that with a data flow programming model that's executed on an in-order engine, right? Does that make sense? Yeah. So data flow at the microarchitecture level provides you latency tolerance by enabling the engine, the hardware, to be latency tolerant. Whereas if you get rid of that, and if you have in-order execution, now you're not latency tolerant at all.
But we have run ahead execution and some technologies to solve this problem. So is it possible to just use existing microarchitecture just to run data flow programs without any modification? We can get the benefits.
So I don't know what you mean by data flow programs.
Okay.
That's,
I need to
yeah, maybe you can.
Yeah.
Maybe you can tell me.
Okay.
You can look into it.
Find out the definition.
Sure. Because there are many, many data flow programs. It could be at the architectural level. But the concept itself, run-rate execution, is another latency tolerance mechanism, certainly. But it's an orthogonal concept. Because you can actually have I haven't looked at this, but you can actually try to do run-ahead execution on data flow engines as well, right? People have actually proposed doing branch prediction on data flow engines, predicting predicates on data flow engines. That's which is interesting, because that way you can actually be more speculative in the data flow. But basically, what data flow buys you is really irregular parallelism. So run-ahead execution cannot get you that either, right? If an instruction is dependent on another instruction, you can find that easily. Well, easily is you can find that with data flow at the microarchitectural level. You can execute any independent instructions in parallel. Okay? Yes?
Doesn't a functional language sort of serves the purpose of a data flow-ish program? Because functional languages are side effect free, are technically all independent of each other as long as they don't use each other's return value. So then the architecture could more easily extract those independencies and execute them in parallel.
That's right. Yeah, that's actually a good point, and that's exactly the reason many of the data flow languages for data flow architectures that were developed early on made use of functional languages. Sisal, for example, single static assignment language. Yeah, Sisal was an important data flow language, and it basically had a lot of characteristics of the functional languages, like no side effects, single static assignment. It's good to think about these. But we haven't covered data flow in detail. We'll get to that at some point, but it's good to discuss this. In 447 we covered it. Hopefully you guys remember, or some of you who've taken 447 last semester. What else? So if you're actually interested in data flow, doing something related to it, I'll give you some references so that you can read. These are references that will be provided later on. Where did I put this?
Actually, you can use this. We've got it working now.
Oh, you got it working? Okay, let's try it, I guess.
Share my screen.
Will I be able to see it?
Yeah.
And where did I put the pen?
I got the pen.
Okay. So I would suggest this paper by John Gourd et al. On Manchester prototype data flow machine.
You want to see this?
This is on CACM 1985, I think. Can you see that? Let's see if I can see it. Not too bad, right? My writing is terrible, so. Is this better? Actually, Manchester prototype data flow computer, it should be. It shouldn't be machine, I think. But that's okay. There's fault tolerance in Google, right? And the other one is by Arvind and Nikhil. That's executing a program in the MIT tag token data flow machine. I'm not going to write this all, but on the MIT tag token data flow machine. These will probably be readings for you at some point. And I think this was in 1990, Transactions of Computers, but don't quote me on that. But yeah, these may be a little bit hard to read, but these show the principles of data flow nicely, I think, data flow at the architecture level. And it talks about, for example, the MIT paper talks about a language called ID that is used to program this machine, which is a functional language. Okay. What else? If you have project ideas other than this, I'd be happy to talk with you about that. So data flow at the architecture level has not been very successful for reasons that we've discussed in 447, because at the architecture level, like if your architecture is data flow, Now, the model of execution is difficult to debug, for example, right? Because at any point in time, how do you know, how do you guarantee precise exceptions? It's difficult to program because at any point in time, your execution can be anywhere. You don't know which instructions have completed, right? The first time you run a program, some instructions may complete, and let's say you get a bug and you're trying to do a breakpoint at some point. The next time you run the program, latencies are different in the entire system, and you may not be able to actually get to that breakpoint. So debugging is extremely hard in this machine. Whereas in a von Neumann machine, debugging is very easy once you have precise exceptions, right? Because everything follows a sequential order. In data flow machine, there is no program counter, right? There is no sequential ordering. In the von Neumann machine, you have the sequential order, and you can say, here's my breakpoint, and this breakpoint will ensure that everything before it will be complete, and nothing after it will be executed. That's very difficult to do in a data flow machine. If you can do it, then you can enable data flow at the architecture level, probably. That's one of the disadvantages. There are other disadvantages in 447 lecture that you can go and take a look at, and we'll probably cover that later on during the semester too. So a lot of the machines today are von Neumann model at the architectural level and data flow at the microarchitectural level. They use data flow principles to extract parallelism. OK. I guess there's nothing else. It took longer than I thought, but this is good. This is exactly the purpose of these recitations, going deeper, discussing. So shall we have a recitation Monday, 7:30? What do you think?
But there isn't much new stuff to cover from here to Monday.
That's right, yes. So maybe we'll reduce that. Yes?
You have to take care of the door because the door gets locked.
That's right, yes. Yeah, we'll take care of that. OK, I guess let's see the results of the poll. Depending on that, it's going to be very unlikely that we'll have a discussion session on Monday. And then we'll see the results of the poll, and based on that, we'll schedule the next one. But I think let's assume for now that the next discussion will be Wednesday at 12:30, which I know some of you will not be able to make. But we'll look at that's exactly why everybody should really fill out the poll, so that we get a good idea of how many people can make the discussion sessions. OK? So please do that, I guess, by the end of today, in the next hour. It's easy to do, right? At least you can see. I cannot see. OK. I guess I'll see you next week.